Okay, now let's take a look at example number 1. We're going to use the trapezoidal rule, which is in part A, and the midpoint rule with n is equal to 5 to approximate the integral from 1 to 2 1 over x dx. Now for part A, with using the trapezoidal rule, we know that n is equal to 5. We know that a is equal to 1, which is the lower limit. We know that b is equal to 2, which is the upper limit. And then we have the displacement, which is equal to 2 minus 1 divided by 5, which gives us 0.2. And so the trapezoidal rule gives us the following integral, from going from 1 to 2 of 1 over x dx is approximately 0.2 over 2 times f of 1 plus 2 times f of 1.2 plus 2 times f of 1.4 plus 2 times f of 1.6 plus 2 times f of 1.8 plus f of 2. And we get the result. We get 0.1 times 1 over 1 plus 2 over 1.2 plus 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 2 over 2. We add those together and multiply it by 0.1. We get an approximate area of 0.695635, again using the trapezoidal rule. Now here is the approximation which is illustrated in this figure. So here are your n is equal to 5 intervals. Now in part B, we want to find the midpoints of the 5 subintervals. And the midpoints of each subinterval is 1.1, 1.3, 1.5, 1.7, and 1.9. So the midpoint rule is going to give you the following. Again, going from 1 to 2, 1 over x. You're taking the displacement, which is 1 over 5. Then you have f of 1.1, which is the first midpoint, plus f of 1.3, plus f of 1.5, plus f of 1.7, plus f of 1.9. And therefore, if we apply that input to that function and add these all together and multiply it by 1/5, we get approximately 0.691908. And this approximation is illustrated in this particular figure by using the midpoint rule. Now, in example 1, we deliberately chose an integral whose value can be computed explicitly so that we can see how accurate the trapezoidal and the midpoint rules are. And by the fundamental theorem of calculus, if we found this integration in our previous sections, we get the natural log of x from 1 to 2, and that gives us 0.693147. Now the error in using an approximation is defined to be the amount that needs to be added to the approximation to make it exact. So from the values in example 1, we see that the errors in the trapezoidal and the midpoint rule approximations for n is equal to 5 are the following. The error for the trapezoidal rule is approximately negative 0.002488, and the error for the midpoint rule was approximately 0.001239. So in general, we have the following. The error of the trapezoidal rule is going from a to b of that function minus t subscript n. And the error for the midpoint rule is equal to a to b of that function minus m subscript n. Now the following tables show the results of calculations similar to those in example 1, but for n is equal to 5, n is equal to 10, and 20, and for the left and the right endpoint approximations, as well as the trapezoidal and midpoint rules. So again, approximations to the integral 1 to 2, 1 over x dx. When the n is equal to 5, you can see what the area is for the left, for the right, for the trapezoidal rule, and the midpoint rule. When we have n is equal to 10, you can see how these numbers are starting to it's getting smaller here, it's getting larger here, approximately 0.69, again approximately 0.69. n is equal to 20, you can see what's happening here. Again, this is getting smaller, this is getting larger. Again, we still got 0.69 and 0.69 for the trapezoidal and the midpoint rule. Now the corresponding errors, you can see what's also happening. Okay, so here's the corresponding error for the left, for the right, for the trapezoidal, and for the midpoint. So you can see what's happening with these numbers. Again, this number is getting larger. This number is getting closer to 0. Same thing here, and same thing here. So we can make several observations from these tables. One of them, in all the methods, we get more accurate approximations when we increase the value of n. But very large values of n result in so many arithmetic operations that we have to beware of accumulated round-off error. Number 2, the errors in the left and right endpoint approximations are opposite in sign and appear to decrease by a factor of about 2 when we double the value of n. 3, the trapezoidal and midpoint rules are much more accurate than the endpoint approximations. 4, the errors in the trapezoidal and midpoint rules are opposite in sign and appear to decrease by a factor of about 4 when we double the value of n. And number 5, the size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. Now the last definition here is the error bounds. So suppose we have the absolute value of the second derivative of that function is less than or equal to k, for x being in between the values of a and b. Now if the error of the trapezoidal rule and the error of the midpoint rule are the errors in the trapezoidal and midpoint rules, then this is the following. The absolute value of the error of the trapezoidal is less than or equal to k times b minus a to the third power over 12n squared. And the absolute value of the error for the midpoint rule is less than or equal to k times b minus a to the third power over 24n squared. Let's apply this error estimate to the trapezoidal rule approximation in example 1. Now, we know that the function f of x was equal to 1 over x. And we know that the first derivative is equal to negative 1 over x squared. And we know that the second derivative is 2 over x cubed. So again, we're using this error bound formula up here. Now, since we know that the lower limits are 1 and 2, therefore x is in between 1 and 2, and we have 1 over x which is less than or equal to 1. So, if you take the second derivative, the absolute value, which is equal to 2 over x cubed, it's less than or equal to 2 over 1 cubed, which becomes 2. Therefore, we're taking k equal to 2, a is equal to 1, b is equal to 2, and n is equal to 5 in the error estimate. We see that for the error estimate for the trapezoidal is equal to k, which is 2, times 2 minus 1 to the third power over 12 times 5 squared, which gives you 1 over 50, which is approximately 0.006667. And if you're comparing this error estimate of 0.0667 with the actual error of about 0.02488, we see that it can happen that the actual error is substantially less than the upper bound for the error given by that equation.